the question 1. Okay, this is for the question 1. So without multi-programming, so the computer system can handle only one process at a time. So if we start with the process 1, then we're gonna actually, the CPU gonna start with process 1 for the time 10 time unit. That's for the CPU bound for 10 time unit, and then switch to the IO for another 10 time unit. And then once the computer finish the process 1, then we start the process 2. So process 2 actually takes about 10 time unit based on the assumption, and then switch to the IO2 for another 10 time units. So the total is 10, 10, 10, 10. Then we can got a 40 time unit. Okay, so that's a total actually time for the for 2 processes. Now let's take a look at the second question. With multi-programming, the total execution time of both processes is, let's see, let's actually just do this similar analysis here. Okay, so okay, in this case, I'm going to eliminate this, erase this, and erase this. Okay, since we support the multi-programming, so when CPU start to pick the process 1, CPU actually execute for 10 time units. Okay, and since it's a single CPU, so for at any particular time, even though the CPU support multi-programming, the CPU still can only execute one process at any particular time. Okay, so we're gonna actually talk a little bit more detail about this, how this actually works. However, since it's actually support multi-programming now after the process 1 complete the CPU bound phase and start to switch to the IO device. Now, in that case, the CPU is actually kind of idle because CPU stopped the execution of the process 1, and the process 1 is now in the hand of IO1. So the CPU is free now. Since the system support the multi-programming, so what the CPU gonna do now? CPU gonna pick the process 2. Okay. So while process 1 is is actually working on the IO, so then the CPU is free, so CPU pick up process 2, and so CPU going to continue with the process 2 for 10 time unit, and at that particular time, the CPU actually complete the process 2, and the IO1 also complete the process 1. So at the time, so process 1 just finished the job. So at the time 20, right? Now, see, also, just the process 2 complete the computer bound phase. So you're going to jump to the IO, and then you're going to run for another 10 time unit. So at that time, so then the process 2 complete the job. So now if you count the total time units, that's 10, 10, 10, that's 30, right? So now see the advantage of using the multi-programming, right? We actually see the advantage of this because the operating system can optimize the usage of the computer resources. While CPU is working on the process 1, then the process 2 has to wait because process 2 cannot directly jump to the IO because in order to actually process to run the IO, you have to actually start the CPU bound phase first, because you have to run the execute the instruction, and then you need to realize, oh, I need IO, you know, then you cannot directly jump to IO. So because without execute, in the CPU. So that's the reason why the question some people may ask, well, why actually CPU is working on P1, why I can directly jump the P2 to the IO2? So then, unfortunately, that's not the case. You have to actually start the CPU phase. But anyway, actually, it reduced the actually total number of times. Okay, total actually time. So what's the total time unit? 30, right? You have any questions on this? Okay, so just interrupt me if you have any questions. Now, the third case, it's a little bit tricky, you know. So if P1 and P2 use time sharing, okay, now technically time sharing is a one of the multi-programming case. Time sharing is a multi-programming, but multi-program doesn't necessarily mean time sharing, because in the time sharing, that means the CPU gonna switch back and forth between multiple processes. Now, time sharing does the same thing, but the time sharing actually, the CPU gonna switch from one process to the other on voluntary basis in the general case. So that means if the CPU is actually execute the process one, now the process one gonna take the CPU. Make no mistake about this. Once a process is taking the CPU, no other process can use the CPU anymore. Because in this particular case, because if you look at this, how the CPU works, the CPU consists of the registers and some actually instruction registers, all these registers. When your CPU start to execute one of the processes, now the register basically stores all the actually variables for these processes. So there's no way that CPU can actually execute the other process, okay, at any particular time. So if you take a snapshot of the multi-programming, it's still the case that the CPU is executing one process at the particular time. However, what the multi-program means, the CPU actually, once a CPU finished the job for this one particular process, or CPU actually in this particular process, it just say, I'm not need the CPU anymore. I want to before I continue, I have to execute the IO resource first. Then I come back and continue with my execution on the CPU. In that case, once the CPU is free, the CPU can pick up another process. So CPU is not uh, going to be idle. So that's the advantage of multi-programming. Now, however, the time sharing is a multi-programming, but it's a very special kind of multi-programming. Now, how this is actually the time sharing is working? In the time sharing, the time sharing is actually controlled by, the switch of the CPU is controlled by the operating system, not controlled by the process. Because in the typical multi-programming, a CPU is running a process one. So, and until the process one finished is done, most of the CPU bound phase, all this instruction for the CPU, uh, then once the process one switch to the IO, then the CPU can pick up some other process. So basically, the process is going to decide whether I'm done with the CPU at this moment, and then free up the CPU so the CPU can pick up some other process. That's general multi-programming. But the time sharing, the control is not on the process side. Now, in the time sharing, typically, the operating system is going to set up, I think it's not probably even not operating system. It's probably the hardware in the hardware design. So the CPU is designed in a way that okay, I can spend certain amount of time on one particular process. Okay, then after this time period of time elapse, then the CPU gonna switch to another process, and then give another process the same amount of time. And then after this time elapsed, the CPU gonna switch to another processes. So that means periodically CPU gonna switch from one process to the other, from one process to the other, and then from one process to the other. And CPU gonna actually switch back and forth among these processes in the currently running in the computer system. So back to this particular case. Now, if P1, P2 uses time sharing, now things are different now. Let's actually take a look at this particular case. Okay. Okay. I don't know, for some reason I cannot erase that. This. Okay. Let me discard this. Switch back. Okay. Let me just completely erase that one. Okay, so now in the case 3, now here's the CPU, IO1, IO2. So now the CPU gonna actually choose to switch back among the process 1. Let's suppose that for the time sharing, the time unit we're gonna use. Okay. It's just, I'm sorry, I'm not going to call it a time unit because that's confusing. Okay, let's assume that the amount of time CPU going to spend on one particular process is 1 time unit. Okay. So this is the amount of time CPU going to spend on one particular process. So let's see. So now we have process 1, process 2. The CPU first, they're going to pick the process 1 and run for 1 time unit. Okay. So then after 1 time unit, CPU going to say, okay, that's enough. You already used your time unit. Okay. And then I'm going to switch to process 2. And the CPU going to spend 1 time unit on process 2 and then switch back to process 1. And then switch back to process 2. Process 1. Process 2. Process 1. And process 2. So this is 1, 1, 1, 1, 1, 1, 1, 1. So process 2, process 1, process 2, 1, 1, 1, 1. So in order to complete the 10 time units of the computer bound phase, okay, in order to complete the computer bound phase of 10 time units, since the CPU switch back and forth between P1 and P2 for every 1 time unit, so CPU gonna actually complete the computer bound phase for P1 gonna be much longer than 10 time units because half of the time it's gonna switch to the process 2. So 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, P1, P2, P1, P2. So 1, 1, 1. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay. P1, P2, P1, P2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now for process 1, it's just to complete the 10 time units of, for the CPU bounded phase. And then the process 1 can switch to IO, right? Once the process 1 switch to IO, now process 1 is no longer compete with the process 2 for the IO or for the CPU. So then the process 2, start, and then process 1 is now in the IO1. So process 1 not gonna compete with P2. So now P2 gonna continue. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually P2 actually finish it, and the P2 gonna start the IO over here, right? Can you see this kind of scenario? Okay. Now this is kind of messy because you're talking about time sharing. So the CPU gonna switch back and forth between processes in the system. Now we have 2 processes. So if the CPU gonna switch after every actually 1 time unit, and this actually 1 time unit is called, mostly it's called a time quantum. Okay, time quantum. Okay, so the CPU gonna spend 1 time quantum on process 1, switch to P2, and spend 1 time quantum on P2, and switch back and switch back, switch back. So it's gonna switch back and forth between P1 and P2. So then after actually switch back like 10 times, the CPU does just finish the P1, and then next time finish the P2. Okay, so now both P1 and P2 gonna spend their entire time on the IO, because process 1 only actually spend on IO1, process 2 only on spend on IO2. So then now what do you think? What's the total execution time of both process?
30 time units.
30 time units. So for this switch back and forth, I believe over here it's already 20. So yeah, 30 time unit in that particular case. One. Yes, 30 time units. So this is actually the case, and because you switch back and forth, so from here to here, that's total 20, right? Time unit. And then let me see. So that's 20, that's additional 10. Yeah, it's 30. It's a 30. So let me actually summarize over here. That's 40, 30. That still looks like a 30. Okay. So this is actually the answer for this. We know that one, right? We know this one. And this is actually, I use different color. The black color represent P1. The red color represent P2. So it's a going back and forth. So 1, 2, 3, 4, 5, 6. Yeah, it's still 30 time unit. Okay. Now, from performance perspective, 2 and 3 are basically the same. But what's the difference between 2 and 3?
I guess you could get like more responsiveness with 3, or like more of like an illusion of responsiveness since they're both sharing the CPU.
Yeah. Yeah. For 2, it's clear that the process 1 immediately get response. So process 1 basically feel like, oh, I'm treated well, right? Because when I start to request for CPU, I immediately get a response. Now process 2 is different story, because process 2 just make a response. Probably actually process 1 make a request for CPU at this moment. Process 2 request for CPU at this moment, and then the process 2 didn't get response until process 1 finished the job, the CPU part of the job, and then the CPU start to treat the process 2. But in this case, the response time is very quick. Process 2 is only just one time unit. Then process 2 get response, say, okay, so the CPU say, I hear your response, and then I'm gonna actually start to actually execute your, treat your request. So looks like it's start, but technically, the overall performance is still the same. Why? Because still actually one CPU running on both processes. So you only actually, schedule time differently, right? On each of the CPU. So it's just like I have two actually in my office hour. I have 2 students come to my office, and then one student actually come in. I spend like 10 minutes with that student on the problems, and the other student has to wait outside. Then in another case, one student is coming, I ask the other student also come, and then during the actually office hour, I actually just talk to the student 1, and then while the student 1 is working on its something, I just say, okay, you think about this way, and then the student 1 is working on this, and then during that free time, I can switch to another student and say, okay, what's your problem? So I can actually switch back and forth between 2 students. Now both students feel like I'm treated well, because you know we I got a response, but technically it's just actually matter of arrangement. So the total amount of time is still going to be the same, right? That's the difference. However, this is actually pretty good. Number 3 is actually pretty good. Now also, when you actually at this moment, I never actually think about the time when CPU actually complete the process 1 and then switch to process 2. That switch is not immediate. Sometimes it takes time, because when you switch from one process to the other, the CPU need to basically clean up the registers in the CPU, and just fill up the CPU, and like a program context, you can start the process 2. So you need time to save the information for process 1 and load the information of process 2 between this time period, and that takes some time. This particular time is called context switch. So if you use a time sharing, then the context switching happens every one time unit, right? So at this moment, when we actually count the total number of times for both process, we ignore the context switching time. But the reality is nothing comes for free, because when CPU actually try to switch back and forth between the processes, and when CPU switch away from process 1, the operating system need to save all the information of process 1 into some place, right? This place sometimes we call the PCB, the process control block. It's a data structure associated with each of the process. So you have to save information of the process in some place, and then you switch to the switch to process 2. And then before you switch to process 2, CPU start to execute the process 2, CPU need to load the information of process 2 into the CPU register. So that basically takes time. So then the time between, between the CPU switching from one process to the other, that's called the context switch. The context switch takes some time. And not much, okay? It's a very small period of time. However, if you have very frequently, you have to frequently change the do the context switching, then sometimes the context switching time is not ignorable. Okay, but now we just choose to ignore that part. We assume that the context switching time is 0. There's no time spent on the context switch, but the reality is there's small portion of the time, for the context switching. So technically, the time sharing, this version, gonna take longer time to finish, because if you add all these context switch time, if you accumulate all these context switch time, because the switch is so frequent, right? So you have to accumulate all these context switch time, and then it still may actually take some time. So after so it's actually take a little bit long, much long. It's a little bit longer time than the case 2. The case 3 probably even actually takes longer time. Okay, does that make sense? Okay, so that's the activity 1.1.7. Okay, now so next, this slide will just actually summarize the two actually process behaviors. One is called computer bound, the other was IO bound. Okay, so computer bound, during the computer bound phase, the CPU basically spend the process, mostly spend on the CPU, and in IO bound is basically spent on the input output devices. Now, for most of the processes, some of the processes actually are IO bound. Some of the processes are CPU bound. Okay. BUND. I just missed the U here. So the computer bound process basically spend more times on the CPU. The IO bound process are basically spend more times on the IO devices. Okay. Now, in some case, in some kind of process, like mostly the computer software that doing the basically doing the scientific computing, most of these kind of process are computer bound. For the IO bound, it basically mostly use the IO. One of the example for IO bound processes is some of the social media software, like chatting. If you use the Lines or Instagrams or any kind of chatting software, and most of the time, you don't use the CPU, but you only periodically, when you type something and hit the enter, then there's actually some kind of burst in the CPU. So that means you suddenly use the CPU to process this message. But most of the time, your CPU is idle. So the computer bound, if you look at the CPU performance, the computer bound most likely looks like this. So most of the time, you actually work on a CPU. Now for the IO bound, it most looks like this. Okay, so if you actually check the your your PC, you check the program manager, and you can check the some kind of the CPU usage. Some of the process going to use the CPU like this. Most likely, this kind of process are I/O bound. Uh, but if you start the computing and you take the CPU most of the time, then that's the computer bound process. Okay, so next thing we're going to talk about is the operating system structure. Um, um, so operating system is a software. So it's not a hardware, it's a software. It's a software that we just talked about. Our operating system is a software that bridges the user and the computer hardware. So it's actually bridging these two actually parts. So it also operating system act like an interface to the user and act like a resource manager to the hardware. So operating system manage all these hardware resources, like manage the CPU, like for example, like in the time sharing, in the multi-programming, operating system actually manage the usage of CPU. Okay. So the operating system is a software system uh, comprising potentially millions of lines of code. So one of the important part of the operating system is the kernel. Okay. The kernel of an operating system is the minimal set of functions necessary to manage the system resources safe and efficient. Okay. Now people may ask, what is a kernel of an operating system? You know, the definition is actually not really. There's no actually unique, a very um, sound definition for the kernel, but most people interpret the kernels like a different way. So in here it says the kernel of an operating system, the minimal set of functions necessary to manage the system resources safely and efficiently. So it's still actually kind of unclear what is the kernel. So take it that way. Suppose this is the operating system. So the kernel is the core part of the operating system. Okay. Or in some other case, people define kernel as the portion, the part of the operating system that's always running. Okay. Okay. So the bottom line is the kernel basically typically provide the most essential service for the memory and the device management. Okay. Creating and managing unit of computations and for communication among different concurrent activity within the system. Okay. So for example, when you run a multi-programming, so then sometimes many times these multiple processes running in the same system, so they need some sort of communication, and that's basically part of the job that the kernel does. Okay. Now to deal with the issues of security, the instruction set provided by CPU is divided into two sets: the privileged and the non-privileged. Okay. So that means when you actually send the CPU, ask the CPU to perform some task, then you need to send the CPU the instruction. Okay. Now, some of the instructions are privileged instruction, and some of these are non-privileged instruction. Now, what is a privileged instruction? A privileged instruction performs critical operation that access I/O devices and the CPU status and the control registers. That's called a privileged instruction. Okay. Privileged instruction basically means that's the instruction that's gonna actually perform some critical job. Okay. So privileged instruction are basically limited to the operating system kernel. Okay, most of the user program, they are not allowed to execute the privileged instruction. So they can send the CPU instruction, but when they actually send the CPU instruction, most of the instruction gonna be non-privileged. Now, what about if the user process, if they try to access the I/O, say one of the process say, I want to use the printer, I want to actually, you know, use some of the scanner or use store some data in part of the memory. Okay, now because access the I/O devices are privileged instruction. Now, if the user want to actually access this, what the user gonna do? So user need to send a request. User need to send a request, and then that request they're gonna ask the CPU kernel to say, okay, here's a request from user to access the I/O device, and then the operating system kernel gonna actually take the control and access the I/O device, perform the service. Okay, so during that time, it's still the actually operating system kernel, controls the access, not the user. User only make a request, and the kernel is still in charge. Okay, so in that case, so that's why the in the operating system we have define any kind of actually uh, so the CPU, we can define two actual mode. One is called the kernel mode. The other one is called the you know um, kernel mode and application mode. So in the kernel mode, then when you actually access some kind of privileged instruction, in that case, in the kernel mode, the kernel is in charge. Okay. Now, the other mode, like when the user try to execute actually certain of the instruction, ask the CPU to, perform the addition, multiplication, and this kind of activity, and that's called a user mode. So okay. So kernel mode basically is a time when privileged instruction is performed. When user mode is basically non-privileged instruction is performed. Okay, that's something we're going to mention again. Um, now, in order to support this, then operating system basically organized into some kind of hierarchical structure. Okay, um, you know, so to guarantee that no programs outside the trusted kernel can use privileged instruction, the CPU operate in two different mode, and this is kernel mode and the user mode. Okay. Okay. So we can actually talk about this a little bit later, but I can actually, so the functionality of the kernel is extended by the set of library which utilize the kernel function to implement high-level system function. Okay. Then additional library provide a wide range of other services to the users. Okay. So the kernel mode only actually, perform the functionality of the kernel and utilize the kernel function to perform high-level system function. And then, so additional library provide a wide range of other service to the user by supporting abstraction above the system call. So when user actually, so we mentioned that the user want to actually access some kind of privileged instruction. The user need to make a request, and that request can be made via some kind of action called a system call. So user can make a system call. The system call gonna actually allow the user to make a request to access the privileged instruction. Okay, now the next one we can actually see the hierarchical structure. Okay, in this hierarchical structure, so at the very bottom, this is actually the device hardware, and here's the CPU. Okay, now CPU can actually basically perform the operation, execute the instructions. Basically, CPU actually receive the instruction and execute the instruction. Now, because we have two sets of instruction, one is privileged instruction, the other part is non-privileged instruction. Now, the privileged instruction only can be accessed by the operating system kernel. Actually, operating system kernel can access both the privileged instruction and the non-privileged instruction. So operating system can access both. Okay. However, if the user, you play the computer game, you're working on your homework on Microsoft Office, and you played Adobe, you play any applications. Now, if the application requests for the privileged instruction, then you need to make a call. Okay. Either from the system call, or the application can directly access the kernel interface. The kernel interface is called a supervisor calls. So in most cases, you go through the system call, and the system call is going to trigger the supervisor call in the kernel. So anyway, you're going to actually go through the kernel. Okay. Now the application can directly execute the non-privileged instruction. So application can directly do this. Or the application can go through the general library and go through the system call to access the non-privileged instruction. So you can access the non-privileged instruction via a different approach. You can directly, send the instruction of non-privileged instruction to the CPU, or you can go through the other interface. Either way, gonna be okay. But to access the privileged instruction, you have to go through the system kernel, the operating system kernel. Now, the operating system kernel is the only operating system component that can access the privileged instruction and allowing most of the application to access the device hardware, the computer hardware, or I/O. That's the reason why we, most of the computer design, there's a hierarchical structure. Okay. Now, this is actually the general structure. Now, if you look at the different operating system, things are slightly different. The Microsoft operating system, Android, and the other operating system like a Unix system, Unix system was a very popular operating system in 1980s and the 1990s. When you actually use a small computer system called actually microcomputer system. Or now, technically, I like the Unix system, or even later on the Linux system or the Android system, more than the operating like a Microsoft Windows operating system, because the Linux system is actually based. The structure of the Linux system is very similar to the Unix system, so it's a very designed hierarchical structure. Okay, it's very nicely designed system. Okay, now the operating system used in Microsoft, like a Windows 10 or Windows 7, Microsoft system is not very, I'm not going to say well designed, but it's it's a little bit messy. It's not it's not as clean as the Linux or Unix or the Android system. Okay. However, Microsoft did a very good job in their marketing, so they can actually eventually sell their operating system very well. But in terms of design, I personally I like the Linux and the Unix or the Android system better than Microsoft. But it is what it is. So Microsoft is very popular operating system in 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 the PC and the laptop area. So okay, so I can actually try to make it quick on this side, the shells. So this is actually pretty much the user interface side. Uh, the shell is actually a user interface that so allow the user to um, you know start interact with the computer system. When a user log in, the operating system starts a graphical user interface or shell. So the graphical user interface is widely used in modern computer system, particularly in the smartphone Android system. So in that case, the user actually doesn't need to know anything about the computer system itself. Everything is provided by the graphical user interface. You actually see all these icons represent different avatars. So if you want to start the program, you just actually double click the icon so you can start the program. So you don't need to type anything. Now the operating system shell is a command interpreter. It's a it's a command line interface that accept and interpret the textual command issued by user via the keyboard. Okay, so this interface is widely used by most of the consumers, most of people who know nothing about the computer operating system or the computer itself, or they don't want to know the details of the computer system. Now, the shell system are widely used. It was used in the earlier computer system, no matter whether you like the computer system or not, because the operating system shell is the only interface to the user. So if you want to actually run the operation, you want to execute any applications, you have to type the command. So and later on, the shell system was when the computer becomes more powerful. So you can actually the memory system is actually memory is bigger and bigger. You can store a lot of actually images. So then the graphical user interface becomes popular, but it's still very popular among the consumers. But the shell is still very used by most of the computer professionals, like IT IT support people, IT admin people. So because the shell actually use less resources because they don't use the graphic user interface, so it takes a smaller actually amount of memory space. And also, if for the admin people, if they want to support the system remotely, so they can log in from their home computer to the server, so then bring the whole graphical interface to your home screen. That requires a lot of bandwidth in your connection, internet connection. But using the shell, you only send a texture, command back and forth between your computer and the server. So the shell is still widely used by the professionals who use to control the server. So this is actually the trade-off between GUI and the shell. Okay. Now this is an example of the Windows operating system. The command line, you can actually use the dir, you use a copy, you use del to delete a file or something. So these are the command. So I'm not going to actually spend much time on this part. So you can actually, if you want to know the detail, you can take a look. So now let's jump to the system calls and a supervisor calls. So system call is a request from the application. So system call is not defined by user. It's defined as part of the operating system. So the user can actually make a system call. We call the system call because it's just like a function call. When you write the computer program, you just like to make a function call. But when you write the computer program, you create your own function. You just call your own function. But system call is the function that are created by operating system. When you make a system call, you are not executing your code. You are executing the code actually written by the system programmer. Okay. So the system call is implemented as a library function which sets up the necessary parameters for the requested operation and the issues and the corresponding supervisor call. And then the supervisor call. That's the kernel call. It's actually implemented in the kernel. It's a privileged instruction. The kernel call, a supervisor call, is a privileged instruction. That's the one you're going to perform the actions on the I/O devices. Okay. So the supervisor call gonna automatically transfer execution control to well-defined location within the operating system kernel. So we're gonna actually talk about this a little bit later because that's a very important. Okay. Supervisor call looks very similar to function call with two special features. The call switches the execution from user mode to kernel mode. Remember, the user mode, in the user mode, the user is in charge, but the kernel mode, the operating system kernel is in charge. So user lost control of the call. So only actually wait for the kernel to respond. Okay. Now also, the supervised call is actually, it's actually the call that basically it's predefined. It's predefined call. When you actually issue a supervised call, it can actually go to a particular location in the operating system and then perform execute the code. So I'm gonna explain this later, maybe not today because we are running out of time, but I'm gonna give you an example of how this actually works, the supervised call. Okay. So basically when the kernel function terminates, when the supervisor terminates, control basically return to the invoking library function in user mode. So that means when the user actually issue a system call, and the system call triggers the supervisor call, and the supervisor call actually execute the code through a table inside. That's something we're going to talk about. And once the supervisor call finish, and the control returns to the user. Okay. Okay, the user can continue with the next operation. Okay. So depending on the type of service provider, control may return immediately or may delayed by blocking or invoking computation to await the completion of some event. So we're going to talk about this later. Some of the call is called when user issue a supervised call, and the user going to be blocked and waiting for the result of the supervised call. In this case, when the supervised call finishes, the control returns to the user immediately. Now, there's another kind of a user system call. So when user requests for system call, and then the system call issue a supervisor call, and the user actually not going to wait for the system call, supervisor call to finish. The user can actually switch to other activity. And in that case, after the supervisor call finish the job, and they're going to issue some kind of things called interrupt. Tell the user, say, okay, your request has been finished. And then the user going to come back and take it. So there are two different scenarios, something we're going to talk about later. Okay. Okay, so I think I'm going to stop the interrupter, but I'm not going to finish this part. Interrupts and the traps. So I think I'm going to spend next Tuesday half of the time talking about interrupts, because interrupt is a very, very important in the modern operating system. Okay, because when interrupt happens, so the operating system gonna actually switch to the interrupter to deal with the interrupter, and then when the interrupter finishes, the operating system switch back to the user. Okay, now modern computers is basically interrupter driven. Okay, now how this interrupter gonna happen? How they and the other actually thing is in trap. Trap is also an interrupter, but the difference between interrupter and trapper is interrupter is basically issued by a computer I/O, the computer hardware. Okay, now trap is typically triggered by software, but both interrupt and trap are going to actually perform exactly the same operation. Okay, so that's something we're going to talk about later, because I think this is actually so important. So we're going to actually, I'm going to spend at least half of the class on Tuesday just talk about the interrupt. Okay. So this is actually most important part in chapter 1. After you finish the interrupt, I think the rest of the topic is going to be very quick. So hopefully we're going to finish let me see. We're going to finish the topics. Let me actually give you some kind of where's my mouse? Okay. So we're going to actually finish the hopefully we're going to finish the chapter 1 next Thursday. So next Tuesday, we're going to actually talk a little bit about the interrupt, and then we're going to actually completely finish the chapter 1 on Thursday, which is February 11th. So what I'm going to do is I'm going to actually postpone the due date for the assignment of chapter 1 to next week. So please actually, you have please spend some time on the weekend, and you can also start the assignments which I haven't covered, but you can actually read the Zybook, and after you immediately read the Zybook, you can practice these exercises. Okay, but I'm gonna cover the topics of the interrupt next Tuesday. So this is a big part, and I'm gonna actually add some material outside the Zybooks, because I want to add some more material, because in the Zybook, the interrupted part is not detailed, so I need to actually add more details on this part. So I'm going to update the course documents on the Blackboard tonight. So please actually, so I'm going to actually change the course document and add a little more material in the PowerPoint. So okay, I think that's pretty much all. So before I actually call it a day, do you have any questions?
So the only homework is going to be the Zybook assignment?
Yes, you can check the Zybooks assignment, and also I can actually put the information on the Blackboard, and so you're gonna work on the Zybook and finish your work, and eventually I'm gonna actually post the grade on the Blackboard. So, but also I'm gonna actually post the information on the Blackboard about any assignments. So, please check back and forth between Zybook and the Blackboard. So these are two most important tools that I'm gonna use throughout the whole semester.
Awesome. I will keep an eye on them.
Okay, great. So that's pretty much it. So if you have any more questions, okay,
Thank you, Professor. See you on Tuesday.
see you on Tuesday. Let me actually turn off the recording.
Yep.